Laws of motion. Learning objectives. At the end of this lesson, students will be able to understand the concept of force and motion, explain inertia and its type, state the three laws of Newton, apply Newtonian concept of force and motion, define force, momentum and impulse, distinguish between mass and weight, analyze weightlessness and the principle of conservation of momenta, explain the law of gravitation and its applications, understand the variation in g height and depth, solve numerical problems related to force and motion. Introduction. Human beings are so curious about things around them. Things around us are related to one another. Some bodies are at rest and some are in motion. Rest and motion are interrelated terms. In the previous class, you have learned about various types of motion such as linear motion, circular motion, oscillatory motion, and so on. So far, we have discussed the motion of bodies in terms of their displacement, velocity, and acceleration. In this unit, let us investigate the cause of motion. When a body is at rest, it starts moving. A question that arises in our mind is what causes the body to move. Similarly, when a moving object comes to rest, you would like to know what brings it to rest. If a moving object speeds up or slows down or changes its direction, what speed up or slow down the body? What changes the direction of motion? One answer for all the above questions is force. In a common man's understanding of motion, a body needs a push or pull to move or bring to rest or change its velocity. Hence, this push or pull is called force. Let us define force in a more scientific manner using three laws proposed by Sir Isaac Newton. These laws helps you to understand the motion of a body and also to predict the future course of its motion. If you know the force acting on it, before Newton formulated his three laws of motion, a different perception about the force and motion of the body prevailed. Let us first look at these ideas and then eventually learn about Newton's law in this unit. Mechanics is a branch of physics that deals with the effect of force on bodies. It is divided into two branches, namely statics and dynamics. Statics, it deals with the bodies which are at rest under the action of force. Dynamics, it is the study of moving bodies under the action of force. Dynamics is further divided as follows: kinematics and kinetics. In kinematics, it deals with the motion of bodies without considering the cause of motion. Kinetics, it deals with the motion of a body considering the cause of motion. Force and motion. According to Aristotle, a Greek philosopher and scientist, the natural state of earthly bodies is rest. He stated that a moving body naturally comes to rest without any external influence on the force. Such motions are termed as natural motion, force independent. He also proposed that the force, a push or pull, is needed to make a body to move from the natural state and behave contrary to their own natural state, called as violent motion. Further, he said when two different mass bodies are dropped from a height, the heavier body falls faster than the lighter one. Galileo proposed the following concept about force, motion, and inertia of the bodies. The natural state of all earthly bodies is either the state of rest or the state of uniform motion. A body in motion will continue to be in the same state of motion as long as an external force is applied. When a force is applied on bodies, they resist any change in their state. This property of body is called inertia. When dropped from the height in vacuum, bodies of different size, shapes, and mass falls at the same rate and reach the ground at the same time. Inertia. While you are traveling in a bus or in a car, when a sudden brake is applied, the upper part of our body leans in the forward direction. Similarly, when the vehicle suddenly is moved forward from rest, lean backward. This is due to any body would like to continue to be in its state of rest or the state of motion. This is known as inertia. The inherent property of a body to resist any change in its state of rest or the state of uniform motion unless it is influenced upon by the external unbalanced force is called as inertia. Activity. Take a glass tumbler and place a small cardboard on it as shown in the figure. Now keep a coin at the center of the cardboard. Then flip the cardboard quickly. What do you observe? The cardboard falls off the ground and the coin falls into the glass tumbler. In activity described above, the inertia of a coin keeps it in the state of rest when the cardboard moves. Then, when the cardboard has moved, the coin falls into the tumbler due to gravity. This happened due to the inertia of rest. Types of inertia. Inertia of rest, inertia of motion, and inertia of direction are the types of inertia. Inertia of rest. The resistance of a body to change its state of rest is called inertia of rest. Inertia of motion. The resistance of a body change its state of motion is called inertia of motion. Inertia of direction. The resistance of a body to change its direction of motion is called inertia of direction. Example of inertia. An athlete runs some distance before jumping because this will help him jump longer and higher. This is example for inertia of motion. When you make a sharp turn while driving a car, you tend to lean sideways. Inertia of direction. When you vigorously shake the branches of trees, some of the leaves and fruits are detached and they fall down. This is inertia of rest. Linear momentum. The impact of force is more if the velocity and the mass of a body is more. To qualify the impact of force exactly, a new physical quantities known as linear momentum is defined. The linear momentum measures the impact of force on a body. The product of mass and velocity of a moving body gives the magnitude of linear momentum. It acts in the direction of the velocity of the object. Linear momentum is the velocity vector quantity. Linear momentum is equal to mass into velocity. V is equal to m into v. It helps to measure the magnitude of a force. Unit of momentum is SI. In SI system is kilogram meter per second and CGS system is gram centimeter per second. Newton's law of motion. Newton's first law of motion. This states that every body continues to be in the state of rest or the state of uniform motion along a straight line unless it is acted upon by some external force. It gives the definition of force as well as inertia. Force. Force is an external effort in the form of push or pull which produces or tries to produce the motion of a static body. Stops or tries to stop a moving body. Changes or tries to change the direction of the motion of a moving body. Force has both magnitude and direction, so it is a vector quantities. Types of force. Based on the direction in which the forces act, they can be classified into two types, as like parallel force and unlike parallel force. Like parallel forces, two or more forces of equal or unequal magnitude acting along the same direction parallel to each other are called like parallel forces. Unlike parallel forces, if two or more equal forces or unequal forces act along opposite direction parallel to each other, then they are called as unlike parallel forces. Action of forces are given in the table. Parallel forces are acting in the same direction. Parallel unequal forces are acting in the opposite direction. Parallel equal force are acting in the opposite direction in the same line of force. Resultant force. When several forces act simultaneously on the same body, then the combined effort of the multiple forces can be represented by a single force, which is termed as resultant force. It is equal to the vector sum of all the forces. If the resultant force of all the forces acting on a body is equal to 0, then the body will be in equilibrium. Such forces are called balanced force. If the resulting force is not equal to 0, then it causes the motion of the body due to unbalanced force. Example, drawing water from a well, force applied with the crowbar, force on the weight, balance, etc. A system can be brought to equilibrium by applying another force which is equal to the resultant force in magnitude but opposite in direction. Such force is called equilibrium. Rotating effect of force. Have you observed the position of the handle in a door? It is always placed at the edge of the door and not at some other place. Why? Have you tried to push a door by placing your hand closer to the edges or the fixed edge? What do you observe? The door can easily open or close when you apply the force at a point far away from the fixed edge. In this case, the effort of the force you applied is to turn the door about the fixed edge. This turning effort of the applied force is more when a distance between the fixed edge and the point of application of force is more. The axis of the fixed edge about which the door is rotated is called as the axis of rotation. Fix one end of a rod to the floor or wall and apply a force at the other end tangentially. The rod will be turned about the fixed point is called the point of rotation. Momentum of force. The rotating or turning effort of a force about a fixed point or a fixed axis is called moment of force about the point or torque. It is measured by the product of force and the perpendicular distance between the fixed point or a fixed axis and the line of action of the force. Torque is a vector quantity. It is acting along the direction perpendicular to the plane containing the line of action of force and the distance. Its SI unit is Newton meter. Coupled. Two equal and unlike parallel force applied simultaneously at two distinct points constitute a couple. The line of action of two forces does not coincide. It does not produce any translatory motion since the resultant is zero, but a couple results in causes the rotation of the body. Rotating effect of a couple is known as moment of couple. Example, turning a tap, winding or unwinding a screw, spinning of a top, etc. Moment of a couple is measured by the product of any one of the forces and perpendicular distance between the line of action of two forces. The turning effect of the couple is measured by the magnitude of its moment. Moment of a couple is equal to force into perpendicular distance between the line of action of force. F is equal to m into s. The unit of moment of a couple is Newton meter in SI system and 9 centimeter in CGS system. By convention, the direction of momentum of a force or a couple is taken as positive if the body is rotated in an anti-clockwise direction. And negative if the rotation in the clockwise direction. Application of torque. Gears. A gear is a circular wheel with teeth around its rim. It helps to change the speed of rotation of the wheel by changing the torque and helps to transmit power. Seesaw. Most of you have played the seesaw since there is a difference in the weight of the person sitting on it. The heavier person lifts the lighter person. When the heavier person comes closer to the pivot point fulcrum, the distance of the line of action of the force decreases. It causes less amount of torque to the action on it. This enables the lighter person to lift the heavier person. Steering wheel. A small steering wheel enables you to maneuver a car easily by transferring a torque to the wheel with less effort. Principle of momentum. When a number of like or unlike parallel forces act on a rigid body and the body is in equilibrium, then an algebraic sum of the momentum in the clockwise direction is equal to the algebraic sum of the momentum in the anti-clockwise direction. In other words, At equilibrium, the algebraic sum of the momentum of all the individual forces about any point is equal to zero. The illustration given in this figure, the force F1 produces an anticlockwise rotation at distance d1 from the point of pivot P called fulcrum, and the force F2 produces a clockwise rotation in the distance d2 from the point of pivot P. The principle of momentum can be written as follows. Momentum in clockwise direction is equal to momentum in the anticlockwise direction. F is equal to, F1 into d1 is equal to F2 into d2. Newton's second law of motion. According to this law, the force acting on a body is directly proportional to the rate of change of linear momentum of the body and the change in momentum taken place in the direction of force. This law helps us to measure the amount of force. So it is also called as law of force. Let m be the mass of an moving object moving along a straight line with an initial speed u. After a time interval of t, the velocity of the body changes to v due to the impact of an unbalanced external force F. Initial momentum of the body P1 is equal to mu. Final momentum of the body Pf is equal to mv. Change in momentum delta P is equal to Pf minus Pi, which is equal to mv minus mu. By Newton's second law of motion, force F proportional to rate of change of momentum. F directly proportional to change in momentum per time. Therefore, F is directly proportional to mv minus mu, which is equal to km into v minus u by t. Here, k is the proportionality constant, where k is equal to 1 in all systems of unit. Hence, F is equal to m into v minus u by t. Since acceleration is equal to change in velocity by time, a is equal to v minus u by time. Hence, we have F is equal to m into a. Force is equal to mass into acceleration. No external force is required to maintain the motion of a body moving with uniform velocity. When the net force acting on a body is not equal to zero, then definitely the velocity of the body will change. Thus, change in momentum takes place in the direction of the force. The change may take place either in magnitude or in direction or in both. Force is required to produce the acceleration of the body in a uniform circular motion. Even though the speed remains constant, the direction of the velocity changes at every point on a circular path. So the acceleration is produced along the radius called as centripetal acceleration. The force which produces this acceleration is called centripetal force. The unit of force, SI unit of force is Newton, and in CGS system its unit is dyne. Definition of 1 Newton. The amount of force required for a body of mass 1 kilogram produces an acceleration of 1 meter per second squared. 1 Newton is equal to 1 kilogram meter per second squared. Definition of 1 dyne. The amount of force required for a body of mass 1 gram produces an acceleration of 1 centimeter per second. 1 dyne is equal to 1 gram centimeter per second. Also, 1 Newton is equal to 10 power 5 dyne. Unit force. The amount of force required to produce an acceleration of 1 meter per second squared in a body of mass 1 kilogram is called unit force. Gravitational unit of force. In SI system of unit, gravitational unit of force is kilogram force, represented by kgf. In the CGS system, its unit is gram force, represented by gf. that is 1 kgf is equal to 1 kg into 9.8 meter per second squared, which is equal to 9.8 Newton. 1 gf is equal to 1 g into 980 centimeter per square, which is equal to 980 dyne. Impulse. The large force acting for a very short interval of time is called as impulsive force. When a force F acts on a body for a period of time t, then the product of force and the time is known as impulse, represented by tau. Impulse is equal to F into t. By Newton's second law, F is equal to delta P by t. Therefore, delta P is equal to F into t, which gives impulse is equal to del P. Impulse is also equal to the magnitude of change in momentum. Its unit is kilogram meter per second or Newton second. Change in momentum can be achieved in two ways. They are a large force acting from a short period of time and a smaller force acting for a long period of time. Examples: automobiles are fitted with springs and sharp observers to reduce jerks while moving an uneven road. In cricket, a fielder pulls back his hand while catching the ball. He experiences a small force for a longer interval of time to catch the ball, resulting in a lesser impulse on his hand. Newton's third law of motion. Newton's third law states that for every action there is an equal and opposite reaction. They always act on two different bodies. If a body A applies a force Fa on a body B, then a body B reacts with the force Fb on the body A, which is equal to Fa in magnitude but opposite in direction. Fb is equal to minus Fa. Examples: when birds fly, they push the air downwards with their wings, that is action, and the air pushes the bird upward, reaction. When a person swims, he pushes the water using the hand backward, that is action, and the water pushes the swimmer in the forward direction, that is reaction. When you fire a bullet, the gun recoils backward and the bullet is moving forward, action, and the gun equalizes this force forward acting by moving backward, reaction. Principle of conservation of linear momentum. There is no change in the linear momentum of a system of bodies as long as no net external force acts on them. Let us prove the law of conservation of linear momentum with the following illustration. Let us have two bodies A and B having masses m1 and m2 moving with the initial velocity u1 and u2 in a straight line. Let the velocity of the first body be higher than the velocity of the second body, that is, u1 is greater than u2. During an interval of time t, they tend to have a collision. After the impact, the body of them moves along the straight line with a velocity v1 and v2 respectively. Force of a body B due to A is given as Fb, which is equal to m2 into v2 minus u2 by 2t. Force on body A due to B is equal to Fa, which is equal to m1 into v1 minus u1 by t. By Newton's third law of motion, action force is equal to reaction force. Fa is equal to minus Fb, that is m1 into v1 minus m1 by t is equal to minus m2 into v2 minus u2 by t, which implies m1 v1 plus m2 v2 is equal to m1 u1 plus m2 u2. The above equations confirms in the absence of an external force, the algebraic sum of momentum after collision is numerically equal to the algebraic sum of the momentum before collision. Hence, the law of conservation linear momentum is proved. Rocket propulsion. Propulsion of rocket is based on the law of conservation of linear momentum as well as Newton's third law of motion. Rockets are filled with fuel in the propellant tank. When the rocket is fired, this fuel is burnt and a hot gas is ejected with a high speed from the nozzle of the rocket, producing a huge momentum. To balance this momentum, an equal and opposite reaction force is produced in the combustion chamber, which makes the rocket project forward. While in motion, the mass of the rocket gradually decreases until the fuel is completely burnt out. Since there is no net external force acting on it, the linear momentum of the system is conserved. The mass of the rocket decreases with altitude, which results in the gradual increase in velocity of the rocket. At one stage, it reaches a velocity which is sufficient to just escape from the gravitational pull of the Earth. This velocity is called escape velocity. Gravitations. Newton's universal law of gravitation. This law states that every particle of matter in this universe attracts every other particle with a force. This force is directly proportional to the product of their masses and inversely proportional to the square of the distance between the centers of these masses. The direction of the force acts along the line joining the masses. Force between the masses is always attractive and it does not depend upon the medium where they are placed. Let us assume that m1 and m2 be the masses of two bodies a1 and a2 placed r meters apart in space. Force is F is directly proportional to m1 into m2, which implies force is directly proportional to 1 by r square. On combining the above two expressions, force is directly proportional to m1 into m2 by r squared, which implies force is equal to g m1 m2 by r squared, where g is the universal gravitational constant. Its value in SI unit is 6.674 into 10 to the power minus 11 Newton meter square kilogram per kilogram square. That is, its unit is Newton meter square per kilogram square. Acceleration due to gravity. When you throw an object upward, its velocity ceases at a particular height and then it falls down due to gravitational force of the earth. The velocity of the object keeps changing as it falls down. This change in velocity must be due to the force acting on the object. The acceleration of the body is due to the Earth's gravitational force. So it is called acceleration due to the gravitational force of the Earth or acceleration due to gravity of the Earth. It is represented as g. Its unit is meter per second squared. Mean value of the acceleration due to gravity is taken as 9.8 meter per second squared on the surface of the Earth. This means that the velocity of the body during the downward free fall motion varies by 9.8 meter per second for every 1 second. However, the value of g is not the same at all points on the surface of the Earth. Relations between small g and capital G. When a body is at rest on the surface of the Earth, it is acted upon by the gravitational force of the Earth. Let us compute the magnitude of this force in two ways. Let m be the mass of the Earth and small m be the mass of the body. The entire mass of the Earth is assumed to be concentrated at the center. The radius of the Earth R is equal to 6,378 kilometers. By Newton's law of gravitation, the force acting on the body is given by F is equal to G capital M small m by R squared. Here, the radius of the body considered is negligible when compared with the Earth's radius. Now, the same force can be obtained from Newton's second law of motion. According to this law, the force acting on the body is given by the product of its mass and acceleration. Here, the acceleration of the body is under the action of gravity, hence A is equal to G. F is equal to ma, which is equal to mg. Comparing both the equation, mg is equal to gm capital M small m by r squared. Acceleration due to gravity is equal to small g is equal to capital G capital M by r squared. Mass of the Earth capital M. Rearranging the equations, the mass of the Earth is obtained as follows. Mass of the Earth m is equal to g r squared by g. Substituting the values of r, g and g, you can calculate the values of Earth as m is equal to 5.972 10 to the power 24 kilogram. Acceleration due to gravity g is equal to capital G capital M by r squared. Variation of acceleration due to gravity g. Since g depends on the geometric radius of the Earth, g is directly proportional to 1 by r squared. Its value changes from one place to another on the surface of the Earth. Since the geometric radius of the Earth is maximum in the equatorial region and minimum in the polar region, the value of g is maximum in the polar region and minimum at the equatorial region. When you move to a higher altitude from the surface of the Earth, the value of G reduces. The same way, when you move deep below the surface of the Earth, the value of G reduces. Value of G is 0 at the center of the Earth. Mass and weight. Mass M. Mass is the basic property of body. Mass of a body is defined as the quantity of matter contained in the body. Its SI unit is kilogram. Weight. Weight of the body is defined as the gravitational force exerted on it due to the Earth gravity alone. Weight is equal to gravitational force, which is equal to m mass into acceleration due to gravity g. G is equal to acceleration due to gravity for Earth at sea level, which is equal to 9.8 meter per second squared. Weight is a vector quantity. Direction of weight is always towards the center of the Earth. SI unit of weight is Newton. Weight of a body varies from one place to another place on the Earth. Since it depends on the acceleration due to gravity of the Earth, G, weight of the body is more at the pole than at the equatorial region. The value of acceleration due to gravity on the surface of Moon is 1.625 meter per second squared. is about 0.1654 times the acceleration due to gravity of the Earth. If a person whose mass is 60 kilograms stands on the surface of the Earth, his weight should be 588 newtons. If the same person goes to the surface of the Moon, he would weigh only 97.5 newton, but his mass remained the same on both the Earth and the Moon. Apparent weight, the weight that you feel to possess during up and down motion, is not same as your actual weight. Apparent weight is the weight of the body acquired due to the action of gravity and other external forces acting on the body. Let us see this from these following illustration. Let us consider a person of mass m who is traveling in a lift. The actual weight of the person is W, which is equal to mg, which is acting vertically downwards. The reaction force exerted by the lift surface or taken as apparent weight is acting vertically upward. Let us see different possibilities of apparent weight or of the person that arise depending on the motion of the lift, upward or downward, which are given in the table. Apparent weight of a person in a moving lift. Case 1. Lift is moving upward with an acceleration A. Case 2. Lift is moving downward with an acceleration A. Case 3. Lift is at rest. And case 4. Lift is falling down freely. At the time, what happens to the apparent weight? The first case, the apparent weight is greater than the actual weight. The second case, the apparent weight is lesser than the actual weight. And in the third case, apparent weight is equal to the actual weight. And in the fourth case, is the apparent weight is equal to 0. Weightlessness. Have you gone to an amusement park and taken a ride in a roller coasters or in a giant wheel? During the fast downward and upward movement, how did you feel? It's amazing. You actually feel as if you are falling freely without having any weight. This is due to the phenomena of weightlessness. You seem to have lost your weight when you move down with a certain acceleration. Sometimes you experience the same feeling while traveling in the lift. Weightlessness of the astronauts. Some of us believe that astronauts in the orbiting space station do not experience any gravitational force of the Earth, so they float. But this is absolutely wrong. Astronauts are not floating but falling freely around the Earth due to their huge orbital velocity. Since space station and astronauts have equal acceleration, they are under free fall condition. Hence, both the astronauts and the space station are in the state of weightlessness. Applications of Newton's law of gravitation. Dimension of the heavenly bodies can be measured using gravitational law. Mass of the Earth, radius of the Earth, acceleration due to gravity, etc., can be calculated with a higher accuracy. Helps in discovering new stars and planets. One of the irregularities in the motion of stars is called wobble, led to the disturbance in the motion of a planet nearby. In this condition, the mass of the star can be calculated using the law of gravitation. Helps to explain germination of root due to the property of geotropism, which is the property of root responding to the gravity. Helps to predict the path of the astronomical bodies. Points to remember. Mechanics is divided into statics and dynamics. Ability of a body to maintain its state of rest or motion is called inertia. Moment of the couple is measured by the product of any one of the force and perpendicular distance between two forces. SI unit of force is Newton and CGS system is Dyne. When force F acts on a body for a period of time t, then the product of force and time is known as impulse. The unit of weight is Newton or kilogram force, kilogram F. The weight of the body is more at the pole than at the equatorial region. Mass of the body is defined as the quantity of the matter contained in the object. Its SI units is kilogram. Apparent weight is the weight of the body acquired due to the action of gravity and other external force on the body. Whenever a body or a person fall freely under the action of Earth's gravitational force alone, it appears to have zero weight. This state is referred to as weightlessness. Concept map. So far, we have learned kinematic, that is divided into static and dynamics. Again, dynamics is divided into was dynamics was taught by three persons: Aristotle, Galileo, Isaac Newton. And Isaac Newton gave first law of motion, second law of motion, third law of motion, and gravitation. The first law deals with inertia and its type. The second law deals with momentum and force. From that, we have the definition of mass and weight. Third law of motion deals with apparent weight, that is weightlessness. The gravitation's universal law of gravitation, variation of G. The end. Thank you.